In the previous video, we have introduced this particular notation, which is called a congruence relation. This notation simply means that the difference between the two numbers on each side of the congruent sign is divisible by the modulus. We have also shown in the previous video that it resembles an equal sign when it comes to addition and multiplication. In fact, by introducing these two operations, we have already stumbled onto modular arithmetic. There are more properties that we can talk about in modular arithmetic, and by looking at them, the congruent sign really behaves like an ordinary equal sign. However, all these properties do not include division, and that is for a good reason. Let's consider this congruence relation. If we divide both sides by 7, we arrive at some nonsense, because these kinds of relations only make sense for integers. So is it that after division, all the numbers are integers, then the congruence relation holds? Let's consider this case. If we divide both sides by 2, even though all numbers here are integers, this is still nonsense. However, this does not mean that we can never do division. Consider another case. If we now divide both sides by 2, this new relation makes perfect sense. So what can we conclude here? Let's just compare the two different cases together. The most important difference is the modulus used. The case that works uses odd modulus, while the case that doesn't work uses even modulus. We can appropriately generalize this to this statement. When dividing by 2 on both sides, we need the modulus to be odd. In fact, we can further generalize this like so. If Ka is congruent to Kb modulo m, then we can divide both sides by k, provided that k and m are coprime. This is our first rule for division. We can prove this pretty easily. Given this congruence relation, then there must exist an integer lambda where this equation holds. We now just write it in another way. Since k and m are coprime, in order for the product on the left to be divisible by m, that means a minus b must be divisible by m. Here, lambda dash is just another integer. So we can conclude that a is congruent to b modulo m. However, this rule of division relies on the fact that k and m are coprime. So what if they are not? We take inspiration from the previous cases again. Although the conclusion does not make any sense, if we tweak it a little bit, it would make sense. Here, 3 is obtained when we divide 6 by 2. When we generalize this, we get the second rule for division on modular arithmetic. This is actually easier to prove. Starting with the given information, we must have this equation when lambda is an integer. By simplifying, we get this ultimate congruence relation we need. However, we are not done yet. These two rules rely on the fact that both sides of the relation have the same factor. What if these two numbers are coprime? The reason we need to consider such cases is that sometimes we will encounter this type of equation, called linear congruence equation. Actually, if you have watched the previous video, you have already seen it. In the previous video, we considered this system of equations. We only focus on the case when all these m's are mutually relatively prime. Now if we ignore the first equation, we would have the solution to be k times the product of all the m's except for m1. Now if we substitute the solution back to the first equation, we have this. For this equation, everything in white is known constants, and we need to solve k. This is basically in the form ax congruent to b modulo m, where we need to solve for x, which is exactly the linear congruence equation we want to solve. You would expect that the answer is x congruent to something modulo m, but we know that we cannot directly do division by a on both sides due to reasons that you have seen before. The more frustrating thing is that we know that a solution must exist so long as all the m's are mutually coprime, and we don't know how to obtain the solution. So what should we do? Again, there are several different cases for us to consider. First, if A and M are not coprime and B is not divisible by their greatest common divisor, then there is simply no solution for this linear congruence equation. This can be proved rather easily. The congruence equation means ax minus b equals m times lambda, where lambda is an integer. Rearranging, we have ax minus m times lambda equals b. If A and M are not coprime, then let's say their GCD is k. Then B has to be k times something. If B is not divisible by k, there is no solution to this, and thus the original equation as well. The second case is where A and M are not coprime, and B is divisible by their GCD. In this case, we could use the second rule of division on modular arithmetic to reduce the case into the third case where A and M are coprime. To tackle this third case, we need something quite tricky. Let's say there is another integer k, so that k times a is congruent to 1 modulo m. Then now if we multiply both sides by k, then we would have x congruent to kb modulo m, which will be the solution. But why does it work? Must there be an integer k so that ak is congruent to 1 modulo m? Yes, and the proof of this is quite involved. Consider the numbers a to a all the way to m minus 1 times a. We claim two things. None of these numbers are divisible by m, and no two numbers here leave the same remainder when divided by m. That means no two numbers here are congruent modulo m. For the first claim, let's suppose ja is divisible by m. Since a and m are coprime, j is divisible by m. However, j should be the values from 1 to m minus 1, none of which should be divisible by m, so there exists a contradiction. Hence, there is no such j in the first place, and so the first claim is proved. For the second claim, again let's suppose IA congruent to JA modulo m. Then I minus j times a is divisible by m. Both I and j are taken from 1 to m minus 1, and so their difference must be smaller than m. And so according to the first claim, there is again a contradiction, and thus the second claim is also correct. With these two claims, consider the remainders when all these numbers are divided by m. Here, 0 is not an option due to the first claim, and no two numbers should have the same remainder. So each number should have a unique remainder from 1 to m minus 1. That means that there must be one number which has remainder 1 when divided by m. So there has to be a number k so that ak is congruent to 1 modulo m, and so this method of attacking the equation works. However, the problem is, of course, how exactly do we find this number? We would use the example here to illustrate the entire process. You can see that 31 and 415 are coprime, and so we can directly go to the third case and figure out the number k such that 31k is congruent to 1 modulo 415. We first consider the continued fraction expression of 415 over 31. And then now, we can consider the penultimate continued fraction convergent. This can be done by using the property mentioned in the first ever video on Mathemaniac. Now, we will consider the products of red and yellow numbers separately. We can clearly see that they are 1 apart. Now what we know is that 31 times 174 is 1 less than the multiple of 415. so we have this negative number on the right side. It is a little weird to use negative numbers, but eventually we are looking for the difference between the two numbers on each side, so we are good here. Now we multiply both sides by -1 and add 31 times 415 on the left side to get this. Finally, multiply both sides by 9 to get this yellow congruence relation. So by comparing with the original equation we started off with, we get x congruent to 2169 modulo 415. This is a valid solution, but you might want to make it smaller. This is done by considering its remainder when divided by 415, so we can get an equivalent solution. If you don't believe me, you can check that this equation is true. As a summary of the entire process, we first considered a continued fraction expression, like 415/31 in the example. Then we consider the second to last continued fraction convergent. It can be done directly or using the property of continued fraction mentioned in the first ever video on Mathemaniac. Then do a cross multiplication to see which product is bigger. Finally, do some polishing on modular arithmetic to get the final answer. For example, in the case above, we need to multiply by -1 before multiplying by 9. To prove that this always works, we still need the property mentioned in the first video. So allow me to copy this property here and consider this expression. Then we simply do some algebraic manipulation. Now focus on these two white boxed expressions. They are basically identical with the subscripts off by 1. That means if we consider the sequence of numbers like this, because we have the negative sign, if we denote the first number as a, then this sequence would be just oscillating with a and -a. But what is the value of a? We first figure out the values of P0, Q0, P1, and Q1. Then we can start calculating a. Now that we know a is 1, that means the original sequence is made up of 1 and -1. That means by doing the cross multiplication between the two consecutive continued fraction convergents, we get either 1 or -1. Actually, we can pinpoint exactly whether it is 1 or -1, but it might be easier to just check the units digit of the cross products. So now we have fully justified why we can use the continued fraction method to find out the solution of a linear congruence equation. In fact, the value of k such that ak is congruent to 1 modulo m is known as the multiplicative inverse of a modulo m, denoted as the power -1. Here, we are not saying k is congruent to 1 over a because this notation is only valid for integers, but since it behaves like 1, we use this notation of power -1. This is similar to the notation of a matrix inverse. We are not saying 1 divided by a matrix, but it again behaves like so we use this notation. So now going back to the rules of division on modular arithmetic, even if the two numbers on both sides are coprime, we can still quote-unquote divide both sides by a number k by considering its inverse modulo m. And of course, k has to be coprime with m, otherwise the inverse of k modulo m would not exist. I understand that this might be a little bit different from the videos that I have previously produced, as this is more like a lecture or a crash course in modular arithmetic, which I admit is boring. but I feel that this video is necessary as a continuation of the previous video, and because not every viewer of mine knows modular arithmetic. The reason I know this is there is a Google form linked in the description that asks for your math levels, and some of my viewers responded. This form is crucial for me to know your math levels so that I know how much detail I need to go into when introducing the background knowledge required for the video. So please fill in that form linked in the description to help me as a content creator. Here is a list of ideas for future videos. I don't know exactly when I will post them, so I don't want to make any promises here. So if you want to see these videos, be sure to subscribe with notifications on so that you don't miss out any of the videos that I will upload. If you enjoyed this video, give it a like, and if you happen to see one of my videos on the suggested, click on it to help support this channel. See you in the next video.